Welcome, boys and girls, somewhere, fathers and mothers that sit to the side of the adult learners. I know you are part and parcel of us, right? So you are all welcome. Feel free as usual. We are being today. We are going to be introduced into another issues about the circle theory, having previously discussed something about the angle properties of the circle. This time around, we are there back to the same circle theory where we'll be learning something about the chord properties of the circle. As usual, I would request you, more especially to some who have just joined us on the way, the videos that need to be followed. So just check on the link and be connected and learn all the videos, right? So that we have to at least finish together the course of Form 3. Without wasting time, let us get into business. Right. As per what I've said, we are going to study something about the chord properties of a circle. Like, so the first thing we need to do is just simply at least try to understand some kind of the relevant parts of the circle. Right, so here may not take much time because most of it we are already introduced in the previous discussion. Check on the previous video about the angle properties of the circle. Right, so what is more important is just a matter of understanding of what it really means about a chord. Right, so here on the parts of the circle for a variable that we're going to discuss about, it's a chord. So a chord is just any line that connects 2 points in the internal parts of what? A circle. Right, so it connects 2 points on the circumference of the circle. Like here, this is my circle. The distance from point may be A, where you move and come back to the same point that is defined as the circumference. So now if I connect any 2 points, like say here I have point T and point H, like that, what I have is the line which is defined like a chord, this one here. So we call TH as the chord. So the whole discussion in this topic is about this line here. Any line that is a chord connecting 2 points on the circumference of the circle like this. Additionally, we will also look at some other variables that are also very important. We talk of the center, O, and also what is known as the radius. Right, so here we're talking of the radius, center, and also what? A chord. Right, so please try to understand what a line, a radius is, what a center is, what a chord is. Things like that. For the radius, I already mentioned that it's a line that starts from the center connecting a point on the circumference of a circle like this. Or H is defined as the radius. Right, so now let's get into business. What is it specifically that we need to learn in this topic? So aside, I have a list of specific objectives that will take us through. Right, because you already know the aim here is at least to have us gaining some skills that can be used in order to work out problems that related to the circle. Right, so here I have a lineup of the objectives. Right, so it's like by the end of the topic, you as students, being the youngsters and the adult learners, you need to know the following, and the must that should be able to describe first the chord properties of the circle. That time it was angle properties of the circle. Right, which are these? One, we need to understand this. That's a perpendicular that can be drawn from the center of the circle to the chord. That perpendicular bisector bisects the chord. Right? Let me come back to that one. A perpendicular drawn from the center of the circle to the chord. That perpendicular bisects the chord. Conversely, it will be true that say if we talk of a line that joining the midpoint of a chord to the center of the circle is perpendicular to the chord. So we're going to discuss that and with some relevant kind of proofs. Secondly, we'll discuss something about not necessarily, we're just going to at least comment as far as much this one is true, then we'll be able to appreciate that a perpendicular bisector of a chord, that one passes through the center of what? Of the circle. So this will be just an obvious thing as much as we're going to know about this. The third objective in our discussion will be about the if two chords are parallel, then the perpendicular bisector of one chord is also the perpendicular bisector of the other chord. So just like if two chords are parallel, it means these chords somehow have a common bisector. As far as this bisector is perpendicular to one chord, it should also be able to be perpendicular to the other. And definitely if this one is bisecting one chord, it means that same perpendicular will also bisect the other chord. Right? So we also need to discuss something about equal chords are equidistant from the center of the circle. We're going to observe that. Let's say if I draw a circle and I have got chords which are equal, we'll be able to observe that, say, these chords will be of the same measure from the center of the circle. Like the distance will be the same. So that's what it means here if talk of equal chords are equidistant from the center of the circle. And we're also going to discuss something about the same, just like the converse of this one, where if you talk of the equal chords are equidistant from the center of the circle, then the opposite will be true. That is to say, chords which are equidistant from the center, they must be what? Equal. Right. So we are there going to prove this theorem and this theorem. Is this really true about this? Because this is about truth. So we always will gain the truth after we have done the proof. Finally, we are going to look about the intersecting chords. Like you have a circle like this one, you find that somewhere the chords may be able to intersect inside the circle like this. So what is the theory that we need to know about this? And how do we put that one into solving of mathematics? Somewhere we also have issues about the chords which are intersecting outside the circle. Like this. Look at this. A chord, this one, extended to point F. And also another chord, which is this one, defined by T maybe X. This one is M, Z, extended to F. TX can manage to go like this and intersect at L, this point here. While this one ends at maybe point D. So I've got chord MZ extended to F and the point TX extended to D. So these ones are intersecting outside the circle. Right. What theory should we know about this? Right. So summary, that's what we'll have to discuss in this topic. So as we are discussing, try to follow by those guidelines. Now, without again wasting our time, because time is more like money, we really have to fetch more. So now here we are going to start right away by discussing the first property about the line that is coming from the center, but it happens that this line is perpendicular to the chord. Right, let us discuss something about that. In the property, which is the theorem we have there, we are referring into all situations of the kind of circle that you can draw of any radius. That is to say, if you are going to draw a perpendicular, that's a perpendicular line. A perpendicular line is just a line that meets the other line at right angles. And this line happens to be perpendicular to the chord, but it's coming from the center. You find that that line is there going to bisect the chord. A situation like this, look here. I have got a circle like this one here. And this is my center O. And here is the chord like this one. I name it chord AB. Right? So if you talk of a perpendicular drawn from the center of the circle to the chord, we're referring to a line, which is the distance from the center to the chord. That line is perpendicular to the chord, like that. Line OX. This line OX will happen always to bisect the chord. Meaning to say, if you draw the line using a pair of, you draw the lines using a ruler and construct the circle using a pair of the compass, you have got this situation. Try to get a protractor and try to measure the value of this angle is 90, that again is 90. Then obviously you'll be able to realize that, say, distance from A to X here will be the same as distance from B1, B to X. So that's what is referred here. A perpendicular from the center to the chord, that is OD, OX, which is perpendicular to AB. This line here will always happen to divide a chord AB in this situation into two equal parts. You expect that AX is equal to what? BX. That's the thing. Right. So now, what we're going to do now here, we are going to prove that if this is really true. By measurements, you can test up by using a ruler, distance from A to X and distance from B to X. Right, you can do that. But remember, construct the circle using a pair of a compass, and also draw the ruler using a draw the line using a ruler, and then a protractor to check the values of angles here. Make sure that they're 90, so that you should be able to deduce that this line is perpendicular to AB. You realize this side is equal to that side. Right, but now in exam we will not be asked to measure. So now, how do we show that really this is true? That line OX being perpendicular to AB divides AB into equal parts, AX being equal to BX. Right. So here we are. Fine. As I said earlier, if you were following me in the previous video about the where we're discussing something about the angle properties of the circle, and we had circumstances where we're proving. I told you that each time you like to prove up a particular concept in maths, if necessary, can you come up with a diagram to summarize your property? So here we would like to prove it's a perpendicular drawn from the center of the circle to the chord, bisect the chord. So what is needed in that first is to draw the circle. In order to summarize this one, a circle is necessary. Now the information in the theory is talking about what? A chord. So definitely, here what you do, draw any chord at any point in that circle. So mine, I'll draw, how is my circle like this one here. So my chord will start from here, that is A to B, like this. So I would say, let my AB be equal to the chord. Right. So what is my aim of doing this? My aim is simply to show that a line from the center to the chord, match that line. There's a condition here. If that line is perpendicular, only perpendicular lines, like this one, that's where you can indicate it. This line here from the center is perpendicular to the chord, like this. At point T, maybe D, like that. Or D is perpendicular to A, B, right? So what does that want to do? We would like to prove that a distance from A to D is the same as distance from B to what? To D. So if BD is equal to AD, then definitely it means the OD has bisected what? AB. And this would be true in all circumstances of the circle that you can draw. Right. So let us now come in. How do we show that? This side AD is equal to side BD. Right. So don't forget the stages which I highlighted earlier in the previous video, that we would like to prove, state what you have been given, and write here like say given. So you can just take the breath as to say the figure as the above. You can state just only important variables within the figure to say where, in this case, we can talk of the O is the center, and talk of the OD is perpendicular to AB, right? This is very important information. The other parts of the figure are not all that very much relevant. So we are asked here to prove what? Simply, if we are going to summarize that statement here, we will refer to the diagram. If we talk of the bisecting a chord, it simply means coming up with the evidence or say the truth about line AD and line BD. Is AD equal to BD? That's what is referred here. Bisects the chord. OD bisects AB, meaning that we have to show that AD is equal to BD. So it is simply just right here to indicate that to prove that AD is equal to BD. That's all. Right. Construction. If necessary, you'd like to add something on the diagram. Right. According to this, we need to add two radii in that circle. Right. One should come from center O joining at B. Another one should start again from center O joining to A. So here we go, like this. Like this. Look with my ruler. It means I'll come like this one. Like that one. That is my constructed line, which is a radius. And again here, I'll have something like this one. Right. So that the resultant figure, it is the figure that contains 3 triangles, out of which 2 are right angled. Right, so here what you do, just take that one to say join, let's say O 2A and B, like this. Join O to A, O to B. So once you have done that, you'll be able to realize that these 2 lines here are defined as radii. Then we know about the radii, formation of which is that the radii are always equal. So what we expect in the diagram here is that this side, AO, should be equal to what? BO. Right, AO is equal to BO, the radii. So let's just have that one in mind. Right, and that one should be carried into the next stage where you need at least to give some kind of evidence to show that AD is equal to BD. So here we go to the last stage where we have got what? A stage where we need to show the activity defined like the proof. So with reference to the figure, we are there now. This is what we're going to do. For us to show that this that again, AD is equal to BD. What is required here? Make that we have constructed O to B and O to A. And we have got 2 triangles here, which are lying side by side with opposite sides. The only way how we can show that this side is equal to this side is by the knowledge that we discussed in Form 2. That's about congruency. So what is needed here, just prove that the 2 triangles are congruent. These are the triangles which have carried the 2 sides. So it's more like they would like just to prove these 2 sides are corresponding to each other and are equal at the end. So you have to remember about the tests that are used to show that triangles are congruent. Just to, in passing, to be fast, we talk of the following test here to show that triangles are congruent. One, we talk of the RHS, that is right angle hypotenuse side. If this side defined by these letters are equal to each other, then the triangle is what? The triangles are what? Congruent. Or talk of SSS, side, 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 meaning that the talk of a pair of 3 corresponding sides are equal, then the triangles are congruent. And you talk of the SAS, that's the side angle side. If a pair of sides and angle, one included angle defined by these letters, are equal, then the triangle is what? Right angled. Sorry, that is what? The triangles are what? Are congruent. Right. The last one, you talk of what? Angle side, angle. If 2 pairs of corresponding angles are equal, and 1 pair of corresponding sides are equal, in any 2 given triangles, then you should be able to expect that the triangles are what? Congruent. So like in our case here, you can see that our triangles here contains right angle. Here there's 90 in triangle OAD that has carried side AD, which is of our interest here, AD, and the triangle OBD, which has carried side what? BD, which is this one here. You'll be able to see that the 2 triangles have got this angle and that angle being 90 degrees. Then obviously, out of the 4 tests that we have here, we are going to first of all test the first one, which has got the talk of the what? R, representing the right angle. Right, so the test that we're going to use here in congruency, we'll first of all go to the RHS. We'd like to show that if 2 right angles are there, and really they're already there, and again a pair of the hypotenuse side are equal, and also the what? Another pair of the other sides are equal, then the 2 triangles are congruent. So in short, we are going to prove that AD is equal to BD by congruency using a test of RHS. So here we go. You write here to say any triangle that is ODA and triangle ODB. I hope you all have knowledge about the congruency. So if you don't have that, maybe you have forgotten some concepts about it, please just try to go back to Form 2 and try to look into it and try then be able to follow what it means by congruency and how we prove that triangles are congruent. Right. So now, let's begin by looking at the idea about R if I'm using this test. R simply means that the 2 triangles contain the right angles. So I'll check in the first triangle here and the other triangle. Yes, here there's 90, here there's 90. It means these two angles are what? Are equal. So it means this one has been satisfied. First letter R has been satisfied. So here I'll write that statement down here like this, as to say angle ODA, angle ODA is equal to angle ODB, ODB. What? You're just going to write what? Given. Right, there's already 90 degrees. Something that is given is already there, just right given. And this one is equal to what? 90 degrees. Right, let us also test the second one, the hypotenuse side. Are the two hypotenuse side of one and the other be equal to each other? So by the virtue of what the diagram that we have them here, you'd be able to realize that the hypotenuse of triangle ODA is the radius, which we have just what constructed. And the hypotenuse of triangle ODB is also the radius, which I have just constructed. So we know for sure that the radii are equal. So in this case, it tells us the two hypotenuse sides are equal. So we write that one down to say side OA is equal to side what? That is OB. This one say radii, just like that. So it means the letter H representing issues about the hypotenuse side has also been satisfied. Then lastly, do we have one pair of sides, corresponding sides in the two triangles equal? Right, so you come and check the diagram as it is there. We haven't been told that AD is equal to BD, but the triangle have got another side, both are defined by OD here. So you can rule out, as much that the triangles are defined by the same side, that is OD, so it's just like OD is equal to OD. So it means the last letter here has already been what? Satisfied. It is described by what? A common side, which is OD, existing to both what? Triangles aside. So in this case, what we write, we just write, say, OD is common. Right. So this one, I'm also going to write that statement here up here, like this. I say, OD is common. Right. Now, what else? It means the three letters which are defining issues about the what? Congruency has been satisfied. Then conclude as to say triangle ODA, this one here, ODA, is congruent. This is the symbol to triangle what? ODB. And you write the reason here in that bracket as RHS. Right. So once we have done that, if the triangles are congruent, then what do we expect? The corresponding sides must also be equal, and corresponding angles must also be equal. Right. So how can you identify that the sides are corresponding to each other? They must be equal. You go to the triangle itself, which is defined by those letters, go by the order of that letters. As far as when you are writing your statements about the test, where in that order, a good order, then you'll be able to depict up which sides are really corresponding to each other. So the moment here you say triangle ODA is congruent to triangle ODB, what it means there? It means if you consider first letter and second letter, you have a side defined as OD. That should also be the same here, first letter and second. It means this side OD is what? Corresponding to side OD. And side DA is also corresponding to side what? DB. By that, second letter, last letter, second letter, last letter. So definitely, in our case, we are looking at issues about AD is equal to BD. So are they in that order? So you find that here, if I'll be able to do this, to go by the same order, in the letters which are defining congruent triangles, it'll be like I'll begin with the last, then go for the second, then here I'll also begin with the last, then go for the what? Second. So in that case, you'll be able to conclude that, say, therefore, AD is equal to what? Talk of what? BD. Right. And then here you write a reason that say these are corresponding sides of congruent what? Triangles. Just by that. So here it means we have really proved that really this line bisects this one. It means this side here is really divided. Right. So we really have to take that, say, when we draw a perpendicular line from the center to the chord, this perpendicular line always bisects the chords. This is the way you can prove it out. Right. Now, what else should we know? The other concept now that we need to know here is that, like now, the converse of this. Like here, when we say a perpendicular drawn from the center of the circle to the chord bisect the chord, then it means the opposite is true, which is the converse of this. To mean that, say, line joining, because D here definitely is the midpoint. Line joining the midpoint of a chord to the center of a circle. Right, that line should always be what? Right angled. Like that is the converse of it. So if you like to prove that one out, very simple again. You can just have it at any other time and have it. But now we can't even waste much time with that. I think can just be done by a discussion which will go like this. Right. Let's plug this one out and look at the converse of what we need to know here about this. Right. So the converse of the first property is this one here, where now it's just going to go the opposite. That's the line joining the midpoint of the chord to the center is perpendicular to the chord. So what we do here, there's no much problems. So you can just like apply the same knowledge similarly. So what is needed here is just a matter of using the same knowledge about what? Converse. Be able to depict the sides which are corresponding to a particular triangle, to particular triangles which are involved in the process of proving. Right, so here, how do I show that a line joining the midpoint of a chord to the center is perpendicular to the chord? So as usual, you come up with the diagram. You begin by drawing a circle, then interpret this one. What does it mean? So what do we have here? It means somewhere we should have what? A chord like this one here. Chord, define it like maybe it's called AB, things like that. And then what? You have to draw a line joining the midpoint of a chord. So take that, say, point maybe M is the midpoint of the chord. Let M be the midpoint. Then if you take the line from here, M to O, like that, what should you expect about this line? What is said in this property is just like this line must be what? Perpendicular to the chord itself. To mean what? At the point this line OM is joining AB, it is the point where the angles of which are what? Right angle. Say this one is 90, this one again is what? Is 90 degrees. Right, so now the truth about it. How do we really show that this one is equal to 90, this one is what? 90 degrees. If this line is joining the midpoint of a chord. Right, so what you do here, I'll just move quickly like this. I like lighting all the stages of the proof. I'll just be quick here. So what we do is simply just doing the same construction. You join O to be like this one, and you join O to what? To A, like that. So you may be able to write what I'm setting out here in the normal way, according to the framework of the proof, like I did earlier. So this one, if I talk of O, B, joining O to A, you can write that information on the stage of the what? Construction, as I did earlier. Right. So now, what is my M? My M here, by this, is simply to show that angle OMB is equal to angle OMA, which is equal to right angles. Or angle OMB and angle OMA are right angled. That's it. This one should be 90, that one is 90. Right. So how would that one be? Right. So I may write just part of that one to say to prove that angle that is OMA is equal to angle OMB, which is equal to what? 90 degrees. The angle of which should be 90 degrees. So now, make that you have joined A to O and B to O. What do you expect again? This one to be what? This side should be the same as that other side. We expect our OA being into what? OB. Why? the early die. As what I mentioned earlier in the proof. Right. If I've shown OA is equal to OB, then what else do I have? I would also be able to realize that, say, we talk of the side OM is what? Is common. You can also write that way. Say side OM is common. Like this. Then after, what do you have there? We're also going to realize that this side here is equal to this side there. That is what? Side AM is equal to what? Side MB. Why? We are told that the M is the midpoint. Right. We are given that. So now, by this, you'll be able to realize that though I have not even told you the test that we're going to use in the congruency here, just by the virtue of the information which I've added in that diagram, you'll be able to see that the test that he's using here to test that the two triangles OMA and OMB are congruent. We go by the information I've added in that diagram. So you see here what I have in this rest here of the first statement, second statement, and third statement. You find that each time I'm talking of the sides. So in the first statement here, I'm talking of OA is equal to OB. That is about the corresponding sides. The second statement here about OM is common. It's talking of this side here that belongs to both triangles. And you can also talk of that one as each about the corresponding sides. And then finally, you also talk of MA and MB. It's also an issue about the corresponding sides. So here is another S. So it means the test that we're using here is what? SSS. Say side, side, side. That's the thing. So in that case, you're going to conclude that, say, triangle OMA is congruent to triangle OMB. Write a triangle OMB. Right, you can write these things orderly as we did with the first one. It's just the converse of that. So I'm just putting into line to what type of information that you need to show that really MO and BMO are right angles. So once you have done this way, then you'll be able first of all to show that the two angles are equal, that this one is equal to this. So this can be stipulated in the triangles themselves by the order of letters. So you find that here, this angle here, which is this one here, is defined as AMO. M is in the middle. And this angle here, by the order of letters, you talk of BMO, which means this one corresponds to this. And this one corresponds to that. This one corresponds to this. So these two corresponding angles, find that they are also there defined accordingly as we're able to go in that order AMO. So I'm talking here, I'll talk about this here to say A, M, then O. You also talk of here what? B, M, talk of this one, B, O, then what? M. Right, so here you conclude as say, therefore, match that this triangle is congruent to that by the test SSS. Then we have it directly that say angle AOM must be equal to angle BOM. These are also corresponding now angles of the two triangles. Right. So if these two triangles are equal, you'd be able to realize here that say, but now if I look at this angle and that angle, the angles which are found on the one straight line. So what do I do there? It means that each time I may be able to think of finding the sum of this and this. That gives me what? 180 degrees. Right. So now you can even decide sometimes upon already mentioning that this is equal to that, you can at least give the notations to these angles, like say, let this one be x1, this one be what? x2, being the same. So what is different there? It means this plus this is 180 degrees. Angle sum on the triangle. So here you come in to say, therefore, angle x1 plus angle x2, where x1 is representing angle AOM and x2 representing BOM in the figure. This one gives us what? 180 degrees. Reason you talk of these are just straight line what? Angles. Right. So it's just like x plus x. So x plus x give us what? 2x. So what you have here, it'd be like 2x is equal to 180 degrees. To find x divided by 2, divide by 2. And what we get here, our value of x is what? 90 degrees. Right. So which means every time you see the value of x in this diagram, that x is represented by 90 degrees. So here, it means this angle is 90, that again is what? Is 90. By that, we are able to accept the theorem that the converse of the first one is to say a line joining the midpoint of a chord to the center. That one must be perpendicular because this is 90, that again is what? Is 90. Right. So that's it about the first property. It is one, but there's a converse of which, and this is the way we prove it out. So having proved this way is when I accept the knowledge and be in the position to apply it into solving some problems. Right, so in this video, this is all what we had wanted ourselves to be introducing the first property and have it that way. So please let us also be together in the next video, right, so that we have to see how we can use this knowledge into solving some problems. So it means the next we'll solve some problems. Thank you very much for being together.